Our last application of the day today is going back to free fall, but this time with air resistance. We got a mass. You could pretend it's a ball falling under the influence of gravity. We got the force due to gravity. If the positive direction is upward, if this is the plus y direction, where y is the height, gravity is in the opposite direction, negative mg. What's the air resistance? Direction-wise, it has the opposite sign of the velocity. If the ball is moving up, so the velocity is upward, positive, then the air resistance is downward, negative. It's going against the velocity. On the other hand, if the ball is falling down, the velocity is negative, the air resistance is upward, it's positive. It's got the opposite sign as the velocity. Now I will draw it going upward just for conceptual clarity in this picture. But realize if I do draw it going upward like that, I'm assuming in my mind that the mass is falling, not rising. If it were rising, the air resistance would point downward. But it does have the opposite sign of the velocity. So you still do write it with a negative sign. Negative some constant times v would seem like the simplest model, saying the air resistance in magnitude is proportional to the size of the velocity, the magnitude of the velocity. Doesn't that seem simplest? Is it right? That takes experiments to figure out if it's right or not. That's part of why we do mathematical modeling. We do our modeling, get an answer, compare it with experiments, see if it worked. If it does, great. If it doesn't, then we need to tweak our model. Is there an example of another model? Some people assume the air resistance is proportional to the square of the velocity instead of the velocity itself. In magnitude, at least, it's still got to be in the opposite direction as the velocity, which makes it a little bit funny. This should seem reasonable. It's a reasonable thing to try. If we try this, then we use Newton's second law. Newton's second law to come up with a differential equation. Newton's second law is F equals ma, where F is the sum of all the forces. So that would be F air plus F grav. That's the total force equals m times a, mass times acceleration. Now plug in what you're assuming F air and F grav are. Negative kv plus, minus mg equals ma. Where's my differential equation? This is a differential equation in disguise because a, by definition, is dv dt. So this equality between this thing and that is your differential equation, your first order differential equation for the velocity. It involves the first derivative of velocity. Now you might say, well, I'm more interested in the height as a function of time. I could write this as a second order differential equation for the height. dv dt would be the second derivative of y with respect to t twice, would equal the first derivative of y with respect to t over there. However, that's not really so handy to do. First of all, first order equations are simpler to solve. Secondly, if we can solve this for the velocity as a function of time, then we could just integrate that to find the height. A direct integral would be good enough. So there's really no reason to think about it in terms of y here initially. It's best just to think of it in terms of v. This is a differential equation. A more standard way to write it would be to divide both sides by m and write dv dt is negative k over m v minus mg over m. And then the m's would cancel here and here. And I write this as negative k over m v minus g. And I've got some initial velocity, v of 0 equals v naught. There's my IVP. Let's think about the slope field of this before we try to have Mathematica solve it. Theoretically, you could solve this by hand with separation of variables, and it is in the reading. You'll see that when you do the reading, in section 11.6, the author of the textbook does solve this by separating variables. But let's think about it with slope fields first. Let's call this f of v. F is not a solution. Phi is what we call the solution. F is just the right-hand side of the first order differential equation. We can use it to figure out what the slope field looks like. In a TV plane, it determines the slopes. Of interest is, are there any equilibrium solutions? Equilibrium solutions are constant functions that solve the differential equation. Their slopes are always 0. dv dt for such a solution would always be 0. To solve the differential equation, it would need to make the right-hand side 0. If I set this equal to 0 and solve for v, I will get an equilibrium solution. First, add k over mv to both sides. Then divide or multiply both sides by m over k. V is going to be negative mg over k. That seems to be an equilibrium solution. It's negative. Does that make sense? If that's negative mg over k, mg and k are all positive. That is evidently an equilibrium solution. What in the world? Why would we get a negative equilibrium solution? Because velocities can be negative, for one thing. And they will be under gravitational force near the surface of the Earth. What goes up must come down. Your other velocities, given by this formula, I haven't written down the formula, are going to go toward that. I'll show you what the graphs look like. They are actually exponential decays toward that. That's different than what happened when there was no air resistance. When there was no air resistance, the velocity graph was a straight line. With air resistance, it's not a straight line. It's got to approach the equilibrium solution, which in fact is a stable equilibrium solution at negative mg over k. What does this mean physically? If this curve were our model based on a certain initial velocity that I'm assuming is positive, take the ball, you're throwing it straight up. What's happening? Right away, the velocity starts getting closer to 0. It's slowing down. At this moment in time, the velocity is 0. You're at the highest point. Then the velocity becomes negative. It's starting to fall more and more negative. It's falling faster and faster. But it's approaching a constant negative velocity. This is called the terminal velocity. Terminal velocity. What does it equal? It depends on whether you are dropping or throwing a rock versus a feather. For a rock, m is going to be relatively large and k is going to be relatively small. Not much air resistance. And this quantity is going to be a big negative quantity. If it's a 1 kilogram mass and k is 0.1, let's use the negative sign, negative 9.8 divided by 0.1, then the terminal velocity is negative 98 meters per second. Maybe realistic for a rock, though you'd have to drop it from pretty high for it to reach that, like from an airplane. Don't drop it from 2 meters high. On the other hand, for a feather, well, first of all, m is going to be small for a feather, maybe 0.01 kilograms. And k might be relatively large. I don't know, 1. The terminal velocity of the feather is negative 0.098 meters per second. What would that be? 9.8 centimeters per second? Is that right? Downward about so fast. That's what the model's predicting. Are formulas for solutions possible to find? Yep. We could do it by hand. And again, the book does do it by hand. Can also use dsolve value. Make appropriate adjustments. I'll copy and paste this code here and make appropriate adjustments to my code. What am I wanting to look at here? I'm wanting to look at my differential equation. Right here. V prime is going to be negative k over m v of t in Mathematica minus g. So make those changes in here. Change the function to v. V prime of t equals negative k times v of t divided by m minus g. I have to emphasize v is a function of t. The initial condition, v of 0 equals v naught. Type it like that. Mathematica does do it. There is the velocity as a function of time. Notice it will be this constant function, the equilibrium solution, if this part is 0. If you factor out the e to the negative kt over m out of that, that'll happen when the initial velocity is, in fact, negative mg over k. If v naught is negative mg over k, that will be 0. And yes, you could take this and figure out the height. How? Just direct integration with respect to t. A logarithm becomes involved. ln, that's actually ln, natural log in Mathematica, becomes involved for the height. Interesting. There'd also be a plus c when you do it by hand. And you'd want to solve for c based on an initial height of y naught. Maybe I can try that here. How could I do that? Let's take that output, plug in t equals 0, first of all. Like that. I'd set this equal to y naught. No, I'd set this plus c equal to y naught and solve for c. Okay, the c for the integration should be this, if I've not made a mistake. Okay, it's complicated, but it's doable. Okay. If you do make the assumption that the air resistance and magnitude is proportional to the square of the velocity, that's harder to solve. And so we'd want to use slope field or Euler's method. Or the slope field is good for giving you qualitative information. What does the slope field look like? Where are their equilibrium solutions? Are they stable or unstable? Euler's method is, or maybe something better than Euler's method, is better for giving good approximations. How long will it be before the ball reaches its highest point, for example? Even in that case where the magnitude of the force is proportional to the square of the velocity instead of the velocity itself.